Hi, my name's Julia Graham, and today I'll be talking about train tracks. Now, in order for me to talk about train tracks, first I have to introduce you guys to tangles and get you to understand a little bit about what a tangle is. Now, a tangle is a smooth, simple, closed curve which is piecewise defined by quadrants of circles, each with the same curvature. And as you can see in our example below, all that means is that the shapes that are created to make our tangles are created by quarter circles all throughout, just in different directions. Now let's get on to our train tracks, the main point of our study itself. Well, what is a train track? A train track is a variation of a planar tangle that includes a combination of quarter circle and line segments, which really helps it stand out as compared to a tangle because a tangle does not allow for line segments. All of the segments of a tangle are all quarter circle segments. Now with a train track, the length of our line segments are equal to the radius of our quarter circles. And all that means is if we were to take the curved segments of our train tracks and straighten them out, they would be of the same length as those straight segments on that train track. Now in the previous picture with the examples, you're probably wondering, well, what's that line, those two dots? Well, that is what we call a dual graph. And so a dual graph is a graph consisting of a vertex for each face or the curved and straight segments of our train track or tangle. It's a configuration with an edge connecting each pair of tangential faces or the faces of that configuration that run along a tangent to one another. And so a dual graph can come in two separate types of links, is what I like to call them. You can have your straight link and you can have your diagonal link. The straight link is able to go vertical as well as horizontal, and they come and they create different shapes for your different train tracks, as you can see in the example below. Now, our train tracks come in different variations. We categorize those by their individual graph or the amount of links within their dual graph. And so below you can see an example of a few amounts of links that can be acceptable for a dual graph of a train track and the different acceptable combinations of those links. And you can combine the different types of links. You can combine the diagonal and the straight links together to create your train tracks, or you can leave them separate and you can add on a diagonal link along onto another diagonal link, as you can see below. Now, another variation that we have within our train tracks are what I call smooth and non-smooth train tracks. Now, a smooth train track has no sharp corners, while a non-smooth train track does. And all that means is that when you're creating the dual graph for your train track and you're drawing that train track itself, if you have two segments that come together and create a notch within that train track, it would be considered non-smooth. And two perfect examples of non-smooth train tracks are our two examples below. And so if I were to try and drive on the route of the top right example, when I come off that curve and I try to go onto that straight segment, I would have to stop or slow down significantly as compared to the speed I was going around that curve. Now, the two bottom examples are perfect examples of train tracks that are smooth. So if I were to drive on the route of these train tracks, I would not have to adjust my speed very much as compared to coming to a stop on the train track above. Now, every study has its different conjectures and the proofs that go along with them. And so for my proofs for train tracks, my first proof is proof 1.1. So let us use M to represent our straight segments and N to represent the curved segments of our train track. If a train track consists of 2M straight segments and 4 times N plus 1 curved segments, then their dual graph is a tree. Now, that being said, that requirement also goes back the other way as well. Now, in order for a train track to consist of 2M straight segments and 4 times N plus 1 curved segments, the dual graph must be a tree. So it has to be a tree in order for it to have those segments, and in order for it to be a tree, it has to have those segments. So you can't have one without the other. Now, in order for a dual graph to be considered a tree, it has to have no cycles. And what I mean by no cycles is that it cannot go back in on itself. So the top left is a perfect example of what I mean. As you can see, there's a link within the dual graph that comes back inside of the dual graph. So after the dual graph has closed its circuit, it continues to go within the dual graph. So if I were to create a train track, I would have to cross over not just the segments of the train track, but I would also have to cross over the links of the dual graph, which would not make the shape that I'm drawing be considered a train track. And the same can be said with the top right example as well. Now, the bottom two examples are perfect examples of train tracks with dual graphs that are trees. Because if I were to draw a train track from these dual graphs, they will not wrap back in on each other or cross segments or lines, which is what a train track does. Now we'll move on to our second proof. So let us assume that the dual graph of our train track is a tree and that it contains M straight links and N diagonal links, and that the train track itself consists of both curved quarter circle and straight segments. So it passes all the requirements to be a train track that we are currently dealing with. Now, such that when M links are added to our dual graphs, we get 2M straight segments added onto our original train track, while adding N links to our dual graphs will add on 4 times N plus 1 curved segments onto our train tracks. And so all that means is every time we add on one straight link onto our dual graph, we'll be adding 2 straight segments onto our train track. Or every time we add on one diagonal link to our dual graph, we'll be adding on 8 curved segments to our train track. And we can kind of also look at these as coordinates. So we can have our M coordinate and our N coordinate. And the equivalent to that would be our 2M coordinate and our 4 times N plus 1 coordinate. If that makes it a little bit easier to understand, our M would kind of be like our X and our N our Y. Now, the only exemption that I have been able to find for our second proof so far is this 6-segment or 6-link train track. And so, as you can see in the example below, our different, when we use those 2 links to close that train track, it takes away 4 of our curved segments, but it only brings back 2 when it's officially closed. So it does not constitute into our 4 times N plus 1 or our 2M. And that's the only exemption I've been able to find so far. I haven't had time to really divulge too far into finding exemptions for the second proof or the first proof itself, because I haven't had time, but hopefully I'll be able to look a little bit further into it and get a chance to understand it a little bit more. Now, along with finding this exemption, there are plenty of other 6-link train tracks that do follow through with the second proof. And so this is really just the only specific case I've found of that. And so there are other six, there are other dual graphs that do create a U that aren't six links that do follow along with the second proof. And then there's this one. Unfortunately, that is all the time I have today for this. Thank you guys so much for your time, and I hope you guys have a wonderful day.